Now, volcanologists will tell you to this day that St. Helens remains the most active volcano in our state, really the one to watch.
Today, Mount St. Helens erupted. 57 people were killed, and it triggered the largest landslide in recorded history.
A startling development has erupted in the shadow of Mount St. Helens, one that has gripped the attention of geologists around the globe. Deep beneath the iconic volcano, a surge of seismic activity and subterranean anomalies has triggered what experts are now calling a red alert, a signal reserved only for the most critical of geological discoveries. What has been uncovered beneath this once devastating stratovolcano is far more than a typical rumble of magma or shifting rock. It's a revelation that could reshape what scientists understand about volcanic behavior in the Pacific Northwest, and potentially around the world. Before we start, smash the like and subscribe buttons for more updates. Mount St. Helens has long been recognized as one of the most active volcanoes in the contiguous United States, infamous for its cataclysmic eruption in 1980. Yet even that monumental event pales in comparison to what is now unfolding underground. A vast, complex magma network has been detected stretching much farther and deeper than previously believed, indicating that the volcano is not merely reawakening, it may be transforming. Recent imaging has revealed a high-magnitude zone of partially molten rock rising steadily from the Earth's mantle, pooling beneath the mountain in a dome-shaped reservoir with extraordinary energy potential. The detection was not a matter of chance. Over the past several months, geologists have been monitoring an uptick in seismic swarms, clusters of small earthquakes occurring in rapid succession, occurring not just at shallow depths but hundreds of kilometers below the surface. This depth was unexpected and alarming. The intensity and regularity of these quakes, many of which exhibited harmonic tremor signatures, a telltale sign of magma movement, prompted researchers to deploy more sophisticated monitoring equipment. When the data returned, it painted a picture of something previously unseen, a deep pressurized magma source that is rising with disconcerting speed. What made this even more unsettling was the unusual composition of the molten rock detected. Using remote sensing and magnetotelluric surveys, researchers found that the magma beneath Mount St. Helens was not only volatile in its mix, but chemically enriched with gases like carbon dioxide and sulfur dioxide in proportions that suggest immense explosive potential. These gases, trapped under tremendous pressure, are what drive the most violent volcanic eruptions on the planet. And in this case, they appear to be accumulating in a sealed environment, building toward a threshold that could, in the worst-case scenario, lead to a high-magnitude eruption unlike anything seen at St. Helens before. The presence of such deep and energized magma deposits reveals that Mount St. Helens is not an isolated geological entity, but rather part of a larger and more interconnected volcanic system than once thought. Scientists now believe that the volcano may be directly linked to other major volcanic centers in the Cascades, including Mount Adams, and possibly even Mount Rainier. This network of volcanic plumbing, a vast underground lattice of molten channels and reservoirs, may mean that pressure in one part of the system could affect others, potentially setting off a chain reaction of seismic or volcanic events. Alongside the deep magma body, another disquieting signal has emerged: ground deformation. Satellite radar interferometry has shown that the Earth around Mount St. Helens is subtly bulging, a clear indicator that magma is intruding into the crust and displacing rock layers. These inflations are measured in millimeters, sometimes centimeters, but they represent powerful subterranean forces. In combination with the seismic and chemical indicators, this ground movement has formed a triad of warning signs that together have prompted the red alert status. One of the most puzzling findings came from an analysis of geothermal anomalies in the area. Thermal imaging detected sudden heat spikes in regions that had long been dormant. These hotspots are not on the flanks of the volcano itself, but extend outward in a radial pattern, suggesting that new fissures are forming, or at least weakening zones in the Earth's crust. Such patterns are often precursors to dome-building eruptions or pyroclastic surges, where a mix of ash, gas, and rock races down the slopes at lethal speeds. The emergence of these heat signals further complicates the already volatile picture geologists are piecing together. Adding to the urgency, gas emissions around the summit crater have increased dramatically. Automated sensors detected a spike in sulfur dioxide emissions, followed by a rise in hydrogen sulfide and carbon monoxide, all indicators of fresh magma rising and degassing. These changes are not gradual but accelerating. Such emission profiles have historically preceded eruptions at numerous volcanoes, from Mount Pinatubo to Geologists. In the context of Mount St. Helens, they point to a system that is not merely awakening but possibly approaching a tipping point. What's particularly concerning is how this activity deviates from past behavior. The patterns observed in 1980, though dramatic, followed a relatively predictable course once the initial signs were recognized. What geologists are seeing now is more chaotic and distributed, with indicators scattered over a larger area and deeper underground. This suggests a broader restructuring of the volcanic system, a shift that could either signal a slow buildup to a major event or an imminent explosion with little warning. Moreover, the depth of the magma source introduces a new layer of complexity. When magma originates from such profound depths, it often brings with it rare earth elements and high-pressure gases that increase the violence of eruptions. The heat and pressure involved can fracture rock far more aggressively, opening new conduits that may not follow previously mapped fault lines. This unpredictability makes forecasting outcomes incredibly difficult, even with the most advanced tools. As geologists interpret this growing body of evidence, one question looms above all others. Is this a prelude to a major eruption, or the start of a longer period of volcanic evolution? While predictions remain cautious, the signs are undeniably urgent. The red alert is not a prediction of an imminent eruption, but a classification that says the volcano has entered a state of heightened potential for hazardous activity. It compels a reallocation of resources, a re-examination of evacuation strategies, and a deep dive into the historical records for parallels. The current scenario also has far-reaching implications for surrounding ecosystems and communities. Mount St. Helens sits amid a complex interplay of natural systems, rivers, forests, wildlife habitats, all of which would be dramatically affected by volcanic upheaval. The influx of ash alone could smother vegetation for hundreds of miles, while lahars, fast-moving volcanic mudflows, could devastate river valleys, infrastructure, and low-lying towns. The Columbia River Basin, a vital commercial waterway, is especially vulnerable to volcanic disruption, and the potential for downstream flooding is a real concern if glacial melt is accelerated by geothermal heating. Air traffic routes would also be severely impacted. Ash clouds from an explosive event could rise tens of thousands of feet into the atmosphere, spreading across jet streams and affecting flights throughout the western United States and potentially beyond. The 2010 Eyjafjallajökull eruption in Iceland, which grounded flights across Europe for days, serves as a potent reminder of how localized volcanic activity can produce global consequences. For researchers, the sudden escalation of Mount St. Helens into red alert status is both a challenge and an opportunity. The data being gathered in real time is invaluable, offering a rare window into the inner workings of a major volcanic system at a critical moment. Instruments placed around the volcano, seismometers, GPS stations, gas spectrometers, are feeding an unprecedented volume of information to volcanology labs. This data may help scientists refine predictive models and develop better early warning systems not just for St. Helens, but for volcanoes around the world. Still, the emotional impact of this discovery cannot be understated. For those who live in the shadow of the mountain, the return of tremors and smoke stirs memories of devastation and loss. In 1980, the eruption killed 57 people and obliterated hundreds of square miles of forest. The knowledge that an even more explosive event could be brewing is difficult to bear. While communication between geologists and local governments has improved dramatically in the decades since, the sense of uncertainty remains. Underneath all of this scientific inquiry and concern lies a more profound realization that Earth itself is never truly at rest. The forces that shape continents, create mountains, and sculpt valleys are continuously at work, hidden from view until they breach the surface in fire and ash. Mount St. Helens is a vivid reminder of this truth, and what geologists have found beneath it is a call to awareness, preparation, and respect. The complexity of this event also opens the door to deeper questions about the Pacific Northwest's volcanic future. The Cascadia subduction zone, a massive tectonic boundary lying just offshore, has long been a source of concern for seismologists. If the magma activity under Mount St. Helens is in any way connected to stress changes along that fault line, it could indicate a broader tectonic shift in the making. Such a possibility is difficult to prove, but it looms large in the minds of those studying these events closely. Beyond the scientific implications, the discovery under Mount St. Helens is a dramatic example of how little is still understood about the Earth's interior. For all the satellites in orbit and sensors in place, the behavior of deep magma systems remains elusive. The Red Alert Declaration is not simply a label of danger. It is a symbol of humility, a recognition that the Earth still holds secrets that can erupt quite literally into our awareness without warning. Every hour that passes brings new information, new challenges, and new questions. The mountain may remain still on the surface for now, but the churning beneath suggests a narrative still being written, one with profound stakes for science, safety, and survival. The red alert has been sounded, not as a cry of panic, but as a command to look deeper, to listen more closely, and to be ready for whatever the mountain chooses to reveal next. As monitoring systems continue to pour in fresh data from Mount St. Helens, a complex and previously underappreciated picture is beginning to emerge. What's becoming increasingly evident is that the geological event underway is not confined to traditional magma pathways or constrained within familiar seismic boundaries. Rather, it appears that the entire volcanic edifice, and the crust beneath it, is undergoing a phase of rapid and dynamic change. This transformation isn't just spatial, it's thermal, chemical, and structural. A metamorphosis occurring in real time, but one that may have taken millennia to prepare. One of the key discoveries linked to the recent Red Alert Declaration involves an anomalous seismic low-velocity zone, LVZ, found beneath the volcano. This LVZ, essentially a region through which seismic waves travel more slowly than expected, suggests the presence of partially molten rock and high-temperature fluids. The broader and deeper this zone becomes, the more it acts as a massive pressurized chamber, primed for movement. And what's truly unusual is the irregularity of its shape. Rather than a simple symmetrical dome, it stretches in several directions like the tentacles of an underground octopus. Such sprawling complexity implies multiple exit points or vents, which means any future eruption could come from more than just the central crater. The surface isn't offering many visual clues, but the ground speaks in other ways. Microscopic cracks and fractures, invisible to the eye but easily detected with ground-penetrating radar and laser mapping, are appearing in patterns that break with known fault lines. These subtle fractures act like pressure release valves, allowing gases to escape unevenly across the mountain's flanks. But this diffusion of pressure, while potentially delaying a singular explosive event, could also be distributing stress more widely, weakening the crust in ways that no eruption model has adequately accounted for. Adding another layer of concern is the presence of hydrothermal alteration zones, regions where superheated fluids have chemically transformed surrounding rock. These zones, now expanding, are softening the mountain's core structure. Hydrothermal systems are common in active volcanoes, but when they intersect with rising magma, the consequences can be catastrophic. The chemically weakened rock can collapse inward under the slightest seismic pressure, leading to sudden depressurization and violent explosions. Such collapses are often silent until the moment they cascade into disaster, making them one of the most feared and unpredictable triggers of volcanic eruptions. Also drawing scrutiny is a newly observed form of episodic tremor and slip activity, low-frequency rumbling paired with imperceptible but persistent crustal movement. This kind of motion, typically found at subduction zones rather than beneath isolated volcanoes, hints at a deeper geodynamic process. If tectonic plates are subtly shifting under Mount St. Helens, the implications extend far beyond the volcano itself. It could signal a redistribution of stress along the larger Juan de Fuca plate, raising flags not only for volcanologists, but for seismologists monitoring the risk of large-scale earthquakes in the Cascadia region. These subtle movements and shifts also correspond with an uptick in electromagnetic anomalies detected by magnetotelluric sensors. These instruments measure the Earth's natural electric and magnetic fields, and recent readings have shown erratic fluxes in conductivity beneath the volcano. Such changes are often linked to fluid movement at high temperatures, a geophysical fingerprint of magma, gas, or superheated water migrating through the crust. More disturbingly, these conductive signals are showing up farther from the volcano than expected, appearing dozens of kilometers from the known magma chamber. This implies that magma may be infiltrating older dormant fractures or establishing entirely new conduits under the radar. Water, too, is playing an increasingly pivotal role in this evolving drama. Glacial melt atop the volcano has begun accelerating due to rising subsurface heat, contributing to an influx of groundwater percolating down toward the magma chamber. This interaction between water and molten rock is notorious for producing phreatomagmatic eruptions, sudden, steam-driven explosions capable of pulverizing rock and blasting debris miles into the sky. The more water that seeps downward, the greater the chance of a violent interface with rising magma. At the same time, an unexpected biological signature has added an eerie, albeit scientifically intriguing, element to the unfolding scenario. Microbial communities that thrive only in extreme heat and pressure, thermophiles and extremophiles, have been found in rapidly increasing numbers in nearby hot springs and geothermal vents. The expansion of these communities serves as a biological indicator of subterranean heating, effectively acting as microscopic messengers from the deep. Their proliferation, in areas previously measured as geothermally stable, offers indirect but compelling evidence of rising thermal gradients below the surface. Technology has advanced to the point where scientists are also employing satellite-based gravitational measurements to detect mass changes in the crust. Recent gravimetric anomalies suggest that not only is magma accumulating, but it's displacing enormous volumes of rock and gas, subtly altering the region's gravitational signature. This method, once reserved for observing ice sheets or tectonic plates, is now being turned toward volcanoes as a powerful forecasting tool. At Mount St. Helens, these readings are becoming more pronounced by the week, signaling that vast internal pressures are building just beneath the calm forested slopes. The implications of these findings extend beyond just geological concern. Urban planners and emergency managers are now being brought into high-level scientific briefings, where simulation models are beginning to depict frightening possibilities. Depending on wind direction, a major eruption could spread ash across major metropolitan areas like Portland and Seattle within hours, disrupting transportation, commerce, and public health systems. Ash inhalation poses severe respiratory hazards, especially for vulnerable populations, and could overload hospitals already operating near capacity. Infrastructure would suffer too. Water treatment plants, electrical substations, and even satellite communications are vulnerable to ash and electrostatic discharge from plume-generated lightning. Further scenarios being modeled include the destabilization of Spirit Lake, the body of water already reshaped by the 1980 eruption. Should a lateral blast or massive debris avalanche occur again, it could lead to a rapid outflow or dam collapse. Such a cascade would send floodwaters and sediment rushing down river channels with devastating speed, jeopardizing communities far beyond the volcano's immediate footprint. The possibility of this kind of cascading hazard is receiving heightened attention, as interconnected natural systems mean the impacts of any major geological event are rarely contained. Meanwhile, academic institutions and national observatories are collaborating like never before. The urgency has broken down many bureaucratic barriers, allowing real-time data sharing across organizations that previously operated in silos. This collaborative push is accelerating the development of AI-driven models trained on volcanic behavior from around the world. By feeding them live data from Mount St. Helens, scientists are testing their ability to detect eruption precursors that human analysis might miss. Subtle frequency changes, minor ground twitches, or gas ratios invisible to the unaided eye. These systems are now running continuous diagnostics, flagging abnormalities with increasing accuracy, and helping prioritize where sensors and field researchers should be deployed next. While the red alert status is primarily a scientific classification, it has psychological effects as well. For nearby communities, it is a source of deep unease. School drills, emergency kits, and evacuation routes, all remnants of a past disaster, are being dusted off and re-examined. Families who lived through the 1980 eruption are once again sharing stories and preparing their children for what might come. Some have begun moving valuables to storage. Others are looking for short-term housing options farther from the danger zone. Local authorities are walking a fine line, trying to keep the public informed without stoking panic, all while staying flexible in the face of rapidly changing science. There's also a cultural undercurrent tied to this reawakening. Mount St. Helens holds spiritual significance for some indigenous communities in the Pacific Northwest. Stories passed down through generations describe the mountain as a powerful and living force, not merely a geological feature, but a sentient presence. These oral histories often include warnings, visions, and metaphors that eerily align with what modern instruments are now detecting. In this sense, the scientific and the spiritual are converging, not in method, but in meaning. Both speak to the awesome, unpredictable power that lies beneath. Even globally, volcanologists are watching closely. If Mount St. Helens does erupt in a significant way, it will serve as a case study for dozens of similar stratovolcanoes around the world, many of which lie near heavily populated regions. Lessons learned here could inform policies, sensor placement, and emergency protocols in places like Naples, Quito, and Tokyo. The volcano has once again become an epicenter, not just of geologic change, but of knowledge, strategy, and adaptation. As the red alert continues and scientists monitor each passing hour for new developments, the region braces for the unknown. Beneath its quiet forests and snow-capped peaks, Mount St. Helens is not sleeping. It is stirring, reforming, and perhaps warning. What lies ahead is not yet written, but every tremor, every sulfurous gust, and every shift in the rock tells a part of the story. A story that is being written in molten stone, in gases older than civilization, and in the restless heartbeat of the Earth itself. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on what geologists found under Mount St. Helens recently? We want to hear from you. Thank you for watching, and see you next time.